There's only half a computer here. Yeah, that's intro slide. There you go. Help. Oh, look at that. Yeah, we're good. Hello, everybody. Welcome, welcome. So I'm going to do a very brief introduction. My name is Nick Isaac. I'm from the UK Centre for Ecology and Hydrology, and I'm co-organising this session with James Pearce-Higgins of the British Trust for Ornithology. The session is called Biodiversity Futures, Harnessing the Power of Scenarios and Models to Reach Nature Positive. And Nature Positive is what is shown in this blue green trajectory here. We're hoping to be able to give the world the choice between, or the tools to choose the happy future, the green trajectory of a world where biodiversity is not declining but increasing. Why are we doing this? Well, governments across the world are trying to make decisions about the actions that they should take for the future. We have the Global Biodiversity Framework with its 2030 targets and its 2050 goals. In England, some of you will have been yesterday at the DEFRA session talking about the targets that we have for the year 2030 to halt the loss of species abundance and recover by 2042. And in Europe now, there's the Nature Restoration Law with a very similar target. So we have a description of what we want the future to look like, and we need to figure out what decisions we need to make now and what actions we need to take in order to get there. And this is really what's motivated a project that we're working on, which we're calling the Biodiversity Pathways Project, but also has motivated researchers across the world. And I'm delighted that we've got several of them here today to talk to us about their work. I've also put a QR code up for a mailing list. I'm really interested in other people who have experience and interest in this area. If you want to join the list, tell us about how engaged you want to be. I think there is an emerging community of practice across the world of ecologists who are interested in this area. So if you are, please let us know. That's enough from me. I'm going to hand over straight away to our keynote speaker. I'm really thrilled to have Damaris Zarel from the University of Potsdam, who's going to talk to us about how to think like a climate scientist.
Thank you. Hi, everybody. Nice to see you all here. Thanks, Nick, for introducing me and for inviting me in the first place. How does that work? Is that my remote here? I suppose so. Right, so Nick suggested that title, actually. I'm hoping that the content is worth it. So I will just provide a broad overview about what kind of models do we have, what kind of forecasts, whereas we have wonderful speakers in the session who will give you a lot more detail. So first of all, the question, why do we need forecasts in the first place? Nick already said that because we want to have improved decision making. We have biodiversity loss, ongoing ecosystem degradation, etc., that have tremendous effects on ecosystem functioning and human well-being, and ultimately also on the climate system. So in order to make informed decisions, we can use models to explore potential futures, or also to do some target seeking, have design the actions that are needed to reach a certain target. This is really in demand for politicians, right? I just give you two examples where politics want numbers, need numbers. We ecologists are often not very good at giving numbers. We are good at saying like, yes, but just providing numbers with a certain confidence and certainty level or uncertainty level, that is something we could still improve on. So that's just an example of extinction estimates that we find in the newest IPCC report. They're actually based on just 2 studies. Okay, one of them was a meta-analysis, but there are not many studies that actually provide these numbers that the politicians want. And the other one, you've probably already seen that earlier, for example, in the workshop on scenarios. That was a brilliant study by Leclerc et al. A couple of years ago, where they used different models to predict how we could bend the curve of biodiversity loss and explored, for example, will conservation efforts be enough? They will be beneficial, but they will only help at halting biodiversity loss. If we really want to bend the curve and improve the state of biodiversity, for example, having increasing populations of vertebrates again, then we also need to change our consumptive behavior and change to sustainable futures. And these ideas actually from that study and another modeling study, they were quite important for driving the goals and also targets that were defined in the Global Biodiversity Framework. Here, well, just summarized as the Biodiversity Plan that was aimed to catalyze, enable, and galvanize policy actions globally, regionally, and nationally. So what we really want is biodiversity forecasts that tell us at different points in time what are the actions that we want to take. So that's a very recent figure by Mike Dietze et al. From the Ecological Forecasting Initiative. I like that a lot. So if we don't have forecasts into the future, we can make decisions, but they're not really informed, right? If we want to make informed decisions also at different points in time, given the best available knowledge about where these decisions would lead us, then we need forecasts. And ideally, we need those forecasts closely integrated with monitoring data so that we have like an iterative learning loop, iterative management or adaptive management where we have real-time environmental data. We use our models to analyze those data, make predictions. We can, of course, then also interpret what we see, get a better process understanding, but then ultimately also make better decisions and then see in the next iteration of time when we validate that with newly incoming data, how well was our decision, do our decisions still take us to the pathway that we want. So one important question then is, how good are we actually at biodiversity forecasting, right? And I like this figure by my colleague Mark Urban that tells us quite nicely that we are lagging behind climate science by at least 20 years. So here he just put up a table of what were important years in the climate science versus important years in climate change biology or biodiversity science and connected those time frames, right? For example, that we had like the first climate conference in the 1970s and the first conference on climate impacts on biodiversity only towards the end of the 80s. And when we look, for example, at the IPCC versus IPBES, IPCC was formed at the end of the 80s. Back then, we already had the first model intercomparison of coupled climate models that were super important for driving the IPCC process forward, for understanding climate change, past, present, future climate change. And when we compare that to the timeline of biodiversity, we see IPBES was only formed in 2012. And we don't even speak of like major modeling efforts yet, right? We still have data and modeling challenges remaining. There are just very few examples of model intercomparison. Ines will talk about the one that just came out this year about terrestrial model intercomparisons. We have a model intercomparison at the global scale for the marine that is from 2021, and that's about it. There's a third one on forest model intercomparison, but I'm not sure whether that was global or just Europe, but that's it really. So we're really lagging behind, and that also means that we are lagging behind in causal analysis, right? Because those models in climate science, they have been really instrumental for detection attribution studies, for switching processes on and off, for comparing predictions against counterfactuals, and step by step they improved their understanding of the climate system and climate impacts on different drivers. And that causal analysis, it's still, well, maybe not in its infancy, but it's definitely lagging behind. So that is also something where we can get better. We did a couple of reviews on where do we stand with those kind of models, and what came out of that was that when we look at all of the applications that use biodiversity models to make predictions for restoration, for conservation, or under climate change, then actually roughly 80% of all those studies are biased towards static models. Then also 80% are biased towards the species level or population level. So by that we are ignoring or naively looking over biodiversity facets that happen within species, intra-species variability, or also things that are happening at the ecosystem scale. And also, almost 80% of the studies are omitting key biological processes and also have no feedback with environmental drivers. What that means is that, of course, we are using environmental scenarios or environmental predictors actually to run our models, but often there's no real feedback, right? Like it's not only that climate and land use is affecting biodiversity, but of course biodiversity could also affect land use decisions, and it could also affect the climate system. When I talk, I don't want to go into all of those different models too much. So I will stay very broadly at the level of talking about static models versus dynamic models. So static models, they basically predict equilibrium states. So they predict what is the environmental suitability for a species or a community, or in how far do the environmental conditions allow certain fitness rates. So it could be, like the most prominent example for those static models are certainly the correlative species distribution models or correlative ecological niche models, but also models like some physiological models. They're mechanistic, but they would also go into that static model type, because they basically just summarize the environmental conditions for a fitness function. So these static models, they predict equilibrium states. They're therefore mostly relevant for telling us something about the abiotic conditions and can be used for in conservation, for example, for assessing climatic suitability, for informing provenancing. Dynamic models, on the other hand, either for single species or multi-trophic dynamic models, they can predict transient dynamics, which is really important to understand time lags, for example. So examples are spatially explicit population models. Greta Bocelli will talk about more of them, but we also have general ecosystem models, and they can really tell us something about the viability of populations or how the ecosystem functioning is developing over time, and therefore can also inform reinforcement of populations, for example. So you could ask, does it better, static or dynamic? I said that 80% of the studies are biased towards static models. I don't want to say necessarily that this is a bad thing or wrong, right? There are reasons for that. So maybe the decision makers are only interested in describing the abiotic conditions rather than describing the population viability of a lot of species for making decisions. But what is for certain is that when we only use static models, we can't predict transient dynamics, or at least we can't predict them very well. When I think of dynamic or process explicit models, then I think of exactly those transient dynamics, right? That they allow me to quantify those time lags. That if we think, for example, of a range shifting species as here. This is the time axis, this is maybe the latitudinal axis, space. Once a driver sets on, then the species is reacting and changing its geographic range, and we might, but it might not do so immediately. So we might find places where the species still occurs, although the climatic conditions or habitat conditions are not suitable anymore. So this is where we could observe an extinction debt, and we might have places where actually the conditions are suitable, but the species doesn't occur yet, for example, due to dispersal limitations. So that is what we typically call a colonization credit. And that could, we could well imagine that this is, or well, actually we have evidence that this is already happening now, right? That a lot of species are not at equilibrium with the environment because they have already been undergoing changes due to climate change. And that also means we could make wrong inferences about what are their environmental preferences, their climatic preferences. So when we see colonization credits and extinction debts in our data, then we may underestimate or overestimate our climatic niche of the species because it occupies climatic conditions or not that are suitable or unsuitable. We also know that including those dynamics into dynamic process models does improve range predictions, right? So that's just a very simple summary of a study that we did with simulated data, virtual data. We had different settings. We had single species settings, multi-species settings. The species were either interacting with the other species in a neutral fashion, so all of them were equal, and the system was very stochastic, given like priority facts and dispersal, or they were interacting with other species in a niche partitioning community. And then we let the hypothetical species run, or we let the simulations run under climate change, took data before climate change set in, calibrated a lot of different models, range dynamic models using those data, then made predictions and compared that against the true virtual reality. And this is what we found. That's the prediction accuracy under current climate and under future climate. So that's basically just the rank correlation row. The higher the value, the better. And we see that under current climate, most of the models, so these are just 5 different modeling families, white are always the correlative niche models, and the colored boxes, they exemplify different model types with increasing complexity. And we see under current climate, all of them are quite good at making predictions, and the correlative models are almost equally well than the others. But under climate change, the correlative models are making predictions that are far worse than for the other models. And that has to do exactly with those time lags that we have, dispersal limitations, that we have interacting species that are blocking the range front, etc. But we also see that even for the dynamic models, the overall accuracy for predicting into the future also decreases over time. We also did similar studies on comparing model accuracy, prediction accuracy, or forecast accuracy for empirical data. That's an example for Swiss breeding birds. Here you actually just see the results for a single bird, the Eurasian skylark, but we did that on 100 species or slightly more. And we compared very simple dynamic models with correlative models. And I don't want to go into the details of which kind of models. What we then did was predicting how well, or we were predicting occupancy dynamics and range dynamics over time and comparing that against our observed data for the Swiss birds. And what we found was that at least for the spatial accuracy, actually the correlative models were often much better than the dynamic models, right? But only when it came to those time series, then our accuracy measures for predicting those temporal dynamics, they were much better for the dynamic models. So dynamic models do improve predictions, but at least in time, but not always in space, right? So there are a lot of subtleties in there. And just to make it, to confuse you all together, here are the results for all of the different models. I don't want to go too much into detail. So that's the theoretical study that I mentioned before, where we had single species, species sorting, so niche partitioning, or neutral dynamics. We additionally tested a lot of different demographic scenarios. The species had long-range dispersal or short-range dispersal. There were contagious disturbances in the system. There were source-sink dynamics in the system. And then we assessed different aspects of predictions. Do they get the range shift right? Do they get the abundance dynamics right? Do they get the rear edge, the front edge of the range correctly, etc.? The only thing I wanted to see here is that we marked which models were best in which situations. The dark square means the winner for the future predictions, and the light square means the winner under current predictions. And you see that those squares are all over the place, right? So that just tells us that there's really no single best approach for predicting biodiversity dynamics, which is why it is so important that we think of model intercomparisons, for example. And also, predictive power today is not indicative of predictive power in the future, right? You may be able to calibrate your model really well to the current data, but it might make good predictions for the wrong reasons. So if you don't have the correct processes in there, then your future prediction might be way off reality. And then there's also the problem of structural uncertainty. Even if we have like a complex mechanistic model, you can still think about which of the processes that I could theoretically include, which ones do I want to switch on or off, and all of those are grounded in ecological theory, so have a meaning, and we should be exploring what would that mean for alternative futures. And we still need improved data integration pipelines. So how do we calibrate those models to data? So where do we go now with that knowledge that we have? That's the GeoBon strategic plan for the next couple of years. GeoBon is the Group on Earth Observation Biodiversity Observation Network. That's like a hidden advertisement for the network, or maybe not that hidden, but I like just like that plan, right? So it says we need improved monitoring of data based on these biodiversity observations together with historic observations that we find in published data and collections. We can then estimate essential biodiversity variables, detect changes in those variables, attribute the changes to different causes, and based on that improved understanding, we can make predictions, we can derive scenarios and forecasts that will then help policy making and decision support. And models are actually quite important at a lot of different stages. So we can use models for guiding future observations. Of course, we need models to do this detection attribution, to run the scenarios and the decision support. So from those reviews that we did, looking at all of those different models, these and summarizing also the model benchmarking that we did with simulated data, these were actually the 5 recommendations that we came up with. So if we want to have a wider use of models in global change research and in conservation, this is what we should do. We should develop easy to use or like advance the easy-to-use toolboxes. We should improve on the calibration and validation. We should develop best practice guidelines of how to use those models. We should definitely work on model intercomparison and ensembles, because they tell us much more about the different processes that may play a role and about uncertainty. And as I said already in the beginning, we should try to embed all that in an adaptive management and monitoring cycle. So just as I still have 5 minutes, I can actually cycle through those things. So just summarizing the first 3 aspects, right? When we compare that to the correlative species distribution models, here, just to give you some numbers, right? There are like 5,000 publications per year that publish correlative species distribution models. So they're just so successful, and maybe we can learn from those for the dynamic models as well. So when we look at, so often people just say they're used so often or so widely because they have comparably simple data requirements. I don't think that this is necessarily the only reason. When we look at the different modeling steps that we have in SDMs, of course we have conceptualization, that is clear, but then we have data preparation, model fitting, model assessment, predictions in space and time. There's just so much guidance and so many packages out there that would help you with all these different modeling steps, right? We have loads of different statistical algorithms and methods available. We have loads of different easy-to-use packages to do that. There are even graphical user interfaces where you just upload your data, you press start, and then you get your predictions. And what is quite important, we have extensive guidance in forms of papers, but also textbooks. We do also start to have best practice guidelines, but they are also still developing. So we could learn from that. We need to have that also in dynamic models. So far it is rare. So Greta will talk a bit more about the range shifter platform that could be such an easy to use toolbox. But when you then want to properly calibrate it, then I have to admit that this is still complicated. So we have done that in a Bayesian calibration cycle where we used prior information and that range shifter framework and monitoring data, then used this prior information to parameterize the model, compared that to monitoring data to estimate the likelihood of observing those data given the model, and then came up with posterior parameters. That was super interesting for us academically, but it was also super successful because that was the prediction that our model gave us. That was the red kite, by the way. So that was what the model predicted with the prior information that we found in the literature on the parameters. And once we've calibrated that, so fine-tuned those parameters, these were the predictions here, so that we just are much closer to our observed data. Model intercomparisons, I don't need to talk too much about it because Ines will do that. So there are a lot of challenges here, just another example of all the models we have with the output they provide, the input they need, etc. So because of that complexity, it will also be very difficult to define and find standardized benchmark data, also at different scales, local to global, define what would be useful standardized experiments and scenarios. And as I said, do that in an iterative cycle. And what I would like to add is that we also need to think about scale, because we're not only talking about global studies, but also local studies, or at least regional studies. Decisions are taken locally. So we need models at all of those different scales. We also need monitoring data at those different scales to compare that to data. Maybe I skip over that. So what I want to say, there are a lot of challenges ahead of us, but also a lot of opportunities. So models really help us to identify what lies in the future and finding that pathway that will lead us to a more desirable future, rather than just looking backward in time. And I think Andy will talk much more about that. If you want to get involved in those endeavors, check out our website. So that's just another advertisement for GeoBon. We have a modeling group within GeoBon called EcoCode, where we really want to develop models for this whole monitoring to mitigation pathway. So from improving monitoring to building indicators, and improving the detection attribution pipeline, and so on. So far from my side, thank you.
So I realise I've been a terrible chair and forgotten to remind people to post questions, but we do have 3 questions. First question is, how close are we to predicting which models will have the most predictive power?
Well, that's an interesting question. First of all, we have to distinguish, like what I said, predictive power today is not necessarily predictive power in the future. So even if we could say which model is better or is making better predictions, we may still want to embrace the uncertainty from the other models. But it is actually quite interesting now that we talk about AI so much, artificial intelligence. I mean, that could be super interesting, at least in guiding decision makers, how you could improve models. If we take all of the papers that, at least those that follow standard protocols, and we train an AI machine on, okay, what modeling decisions do you take in which situations to make good predictions? I mean, that could be super helpful. And then we could also predict which decision at least is most helpful at making good predictions.
So that actually leads on really nicely to the next question, which is about uncertainty and accuracy. And so shouldn't these also be important considerations?
What was that, as uncertainty and accuracy?
Yeah.
Yes, they are important considerations. We have to, I mean, when we think of ecological models, there are different things we may want to consider. That's precision, that's realism, that's generality, and yeah, I can only repeat myself. Like I would always advocate for comparing different models that are plausible, not necessarily all models, but models that we think are plausible, that we can justify well, in order to then properly compare the uncertainty. Because some models will make more accurate, more precise predictions now, but maybe we do want to have other models that include mechanisms to make more general predictions into the future. Like, there will always be those trade-offs, and I would embrace them.
Thank you so much. Thank you so much to Damaris. Those of you on the ends of the rows, could you please move in a bit so that the folks on the stairs can have a slightly comfier time of it? So our next speaker is Anita Lazurko, who's from UK Centre for Ecology and Hydrology. And Anita's talk is about the power of scenarios and using the future to change the present.
Excellent. Okay. Hi, everyone. Very nice to see so many of you here. Like you said, my name's Anita. Some of you were maybe at the workshop previous, so this will hopefully be different enough that you aren't sorry that you're listening to me speak again. I am, just by way of introduction, so you know where I'm coming at all of these questions from, I'm a scenario developer at the UK Centre for Ecology and Hydrology, and I call myself kind of undisciplinary or transdisciplinary in that it's very much about bringing these processes together. So I was trained in a transdisciplinary PhD in more kind of systems analysis and scenarios or futures-oriented work. And that's really focused on processes of knowledge integration, so how you bring diverse disciplines, stakeholders, models together that operate in different data types, sectors, and scales to try to make sense of really messy problems. And one of those problems is this challenge of biodiversity and biodiversity loss. So Nick mentioned the Biodiversity Pathways project, so I won't go into it here, but that's the project that brought me here into this topic, which has been really enlightening and fun. And I hope to do more of this kind of work in the future that is related to this graph that we keep seeing over and over and over again, but I think that's because it just paints the picture so well. Earlier today, I kind of did an introduction on these scenario methods for looking at a broad scope of futures, but today now I'm going to really focus on this kind of green line, how we can use scenario methods to try to get at these desired futures and in that preferable zone. And so, sorry for those who were there, but I'll just repeat this. This is a way of thinking about the future and how we kind of do so in the scenarios world, where we have now and time moving forward and everything beyond the present moment. We have this basic extrapolation or a perpetual now that's more business as usual. And beyond that, based on our current trends, we might be able to project likely futures and assign some probability. And that's sometimes where we stop, but there's a lot more. We might be able to project some plausible futures. We don't know enough to assign probabilities. Maybe the systems are too messy, but it could happen, and it's worth considering. And even beyond that, there's possible futures associated with knowledge that we may not hold today, or we may not quite understand yet, but that we might obtain in the future and can help us explain what's emerging. And beyond that, there's the preposterous futures, which we just say won't happen. And yeah, depending on who you talk to, they'll have different opinions about where that preposterous zone exists. But like I said, I want to talk about the preferable zone, and that is this green zone here. And I think, I spoke earlier about how moving outward to a wider scope of this future potential beyond kind of this basic extrapolation means different degrees of uncertainty, wider system boundaries, and different forms of knowledge that need to be brought into this process. And even though that's messy, it doesn't mean it's not worth exploring, especially because, arguably, lots of our preferable futures, many people might cast aside as implausible right now. So we need to kind of step outside of that mindset and try to think a bit more broadly. And that requires, like I said, kind of new forms of science or emerging forms of science and knowledge that really try to integrate multiple forms of evidence to try to make sense of that preferable zone, pathways toward it, and really kind of motivate that action. And so to ground this in something that is a little more literature-based, there are colleagues working in transdisciplinary research that offer us a way to think about how these new types of knowledge relate to our existing forms of science. So there is system knowledge, which is what is. This is analytical and descriptive knowledge about the actual state of the system. And we are very good at developing system knowledge, and many of you probably do that in your day-to-day, and I've done lots of that. But there are other types. Target knowledge, or what ought to be, is knowledge about the desired future developments of the system. So this brings in value judgments, this brings in people with a stake in the future system, and metrics by which we say something is good. And that kind of target knowledge is often different than system knowledge. And lastly, there's transformation knowledge, or how to. So this is knowledge about how we can move from the actual state to this more desirable state. And I think, this is in the context of transdisciplinary research that's trying to produce action-oriented knowledge. And that is, in these two domains where we kind of need to start looking at that green, bending the curve, and producing this type of target and transformation knowledge that is kind of less, I suppose, dominant. And sorry, I need to segue here. And developing this type of target and transformation knowledge really requires both very established means of operating and doing science alongside some new capacities that can be brought into the scientific process. And so there are lots of those, but I'll give a few capacities here. One of those is imagination. This is a science fiction author, and she said, if you look back 60 or 70 years from now and think of people who might have been trying to imagine the world we're in today, it is unimaginable. Even the people who are most connected to technology would not imagine what the internet has done to change it. And there's a lot of writing now of the role of imagination in sustainable futures and also in the science for sustainable futures. The next is vision. So Donella Meadows, many of you will know who she is, author of Limits to Growth, wrote all this amazing stuff on systems thinking. In 1983, she presented this to a conference of integrated modelers in Costa Rica, which was probably very scary to say at the time, but really important, where she was saying, if we don't know where we want to go, it makes little difference that we make great progress. Yet vision is not only missing almost entirely from policy discussions, it is missing from our whole culture. We talk about our fears, frustrations, and doubts endlessly, but we talk only rarely and with embarrassment about our dreams. And the last thing, which is perhaps a bit less tangible here, is the idea that we need to bring together multiple evidence bases. And there are lots of people in the biodiversity community trying to do this. The figure on the right is showing the integration, kind of weaving together of natural sciences, social sciences, local knowledge, indigenous knowledge, practitioner knowledge, and doing so to try to develop this enriched picture of something that is too complex to understand on its own. And in doing so, each knowledge system is allowed its own integrity. And I think that's where this kind of, the ethics of this come into play, but also the fun and the kind of the messy joy of these types of research processes. In our work, what we use very often is kind of as a place for all of these things to coexist and live together is to do some scenarios and pathways processes. So we use scenarios as a tool for producing knowledge about these transformative options. Scenarios are these descriptions of the potential future trajectories of a system, and they can be represented in a lot of different ways, narratives, numbers, etc. But like I said earlier, there are not predictions of what the future will look like, and contrary to our workshop earlier, they're not just a 2x2 matrix method. There's a lot of other ways to do it. I showed this earlier as well. This case study I'm about to present is living in this target-seeking world. So these are desirable futures and what we want to happen. So we're not trying to predict the whole scope of future uncertainty. We're trying to ground things in getting to a nature-positive pathway. And I'm going to have to go quickly because I spoke too much earlier, so bear with me. The BioNext project is a really interesting Horizon Europe project that we at UKCEH are working on. That's looking at transformative options to mainstream biodiversity across policy sectors. So trying to situate biodiversity in this nexus of water, food, climate, energy, transport, and health. There are a bunch of objectives. The main ones that I'm working on and that I thought you might find interesting is the top 3. So we're trying to co-create scenarios of plausible futures and desirable nature-positive visions for Europe to 2050. We're trying to co-create a set of just transition pathways for achieving those visions and to develop and evaluate those pathways via a nexus modeling framework. And so our approach to using scenarios to inform this whole process is quite iterative. So here's another now to 2050 and scale of action. So the first thing we did is a year and a half ago. We had a workshop with a bunch of stakeholders across Europe, from a bunch of different sectors, all kind of working at the EU level, to develop exploratory scenarios of where we're heading, generally bad for biodiversity, as you can imagine. And then we looked at developing nature-positive visions of where we want to be, and I'll present more on that. Then this year, we went to the Netherlands to develop just transition pathways, where we tried to look at where action would take us. And then we're in the process now of modeling those, and I'll show you about the framework briefly later. But what we suspect is that there'll be a gap between where their actions that they propose are taking them and where they actually want to go. So we'll have another workshop where we'll up the ambition of those pathways, reinforce them, address gaps, etc. And that's all leading towards some recommendations on transformative action and an app and all sorts of fun outputs. Oh no. Okay. So very briefly, we used the Nature Futures framework, which Natalie presented yesterday, to inspire the creation of 3 different visions for the future of Europe, nature-positive visions for the future of Europe, each underpinned by the value perspectives on the Nature Futures framework. So we did this kind of co-creative process, and we did a nexus analysis to try to enrich those visions with positive synergies between different sectors and biodiversity, so trying to make it kind of a coherent future. And we translated those visions both into art, which is in the top right, a bunch of different formats, narratives, etc., but also we translated those into vision indicators. So how do we know, according to our models and other forms of evaluation, whether we've met those visions? The transformative pathways were developed in another co-creation workshop. This was led by the Dutch Research Institute for Transition, so they have a lot of social scientists who do work in transition theory and stuff, so it was a really fun and really creative process where we brought in a lot of both kind of systems analytical and imaginative methods to try to get people kind of out of their normal way of thinking. And again, narratives translated into then model input parameters, which we're now in the process of evaluating using this nexus modeling framework. And I'll admit this is what I'm less familiar with, but I can speak generally about it. We have 3 models that are part of this nexus modeling framework. There's the integrated assessment platform, which is a dynamic integrated assessment platform for the whole of the EU. Crafty Europe, which is an agent-based model, kind of land use, and then a new Juniper system dynamics model. And these are all modeling these pathways, and then we'll be looking at their outputs to see whether they achieve the vision. And we're combining that, you can't model everything, so we're not going to discard the things we can't model. We're doing kind of a parallel evaluation of those non-modelable aspects and kind of synthesizing that together to then reflect on this question of what do we need to do to really up the ambition of these pathways to get them more ambitious, essentially. I'm probably out of time, so I will just briefly say, achieving nature-positive futures, I think, requires us to develop target and transformation knowledge, not only system knowledge, even though all 3 of those are very important in this whole process. And we need to kind of embrace a diverse and integrated set of scientific skills, methods, and expertise. And this kind of process I showed where you're linking these co-creation participatory activities with different disciplinary expertise and integrated modeling can really be a way to leverage those multiple evidence bases and kind of co-legitimize the whole thing in the eyes of decision makers in ways that can be, I think, hopefully informing some transformative change. So thank you so much. Sorry I spoke so quickly. I felt a little bit of time pressure, but I'll hand it over to Nick.
Thanks so much, Anita. So we've got one question, and the question is, how much research attention do we give to communicating nature-positive visions as we have seen socially beneficial visions, such as the 15-minute cities, being negatively targeted in the political discourse?
That's an interesting question. Was the question how much do we, or is it kind of like
Yeah, is that
pondering,
something,
like, is
is
this
that
something that we
considered
want to do?
research?
Yeah.
I guess it's the targeting of political targeting of these kind of visions.
Yeah, I suppose there's like a risk of co-option of most things that you put on the internet. So I'm not really sure how to answer that. I think my worldview is that, you know, we're kind of creating the futures we can imagine. So if the stuff that we have out there is uninspiring and sad, it kind of sucks. So if we're doing all this work to bring people together, to imagine something, and people pour their hearts into these processes, which they do, like I've never seen such an engaged group of stakeholders, then I think sharing that and what it represents is important. I suppose I could be wrong and maybe naive. I don't know.
Okay, cool. Thank you so much, Anita. So our next speaker is Andy Purvis, and Andy's going to talk about biodiversity indicators and, in the context of targets, why we need a sat-nav for nature.
Thanks very much, Nick, and thank you everyone for coming. I'm just saying, that does work. Right, got no excuse. Coffee level adequate. Good. And also thanks to my collaborators on the Predict project and Glitters. They're two projects that really kind of shaped my thinking about this topic. And does this work? Yes, it does. Right. So, coming at indicators from wanting to be able to set goals and targets. So, Damaris was sort of urging us to learn from climate scientists, and here's, in very broad, simple terms, how they set goals and targets. We've got a bunch of scenarios, the shared socio-economic pathway scenarios, with different levels of radiative forcing, which is what those numbers are. And they lead to different amounts of climate change by 2100, and we look at these scenarios' outcomes, society, stakeholders, politicians. IPCC spells out the likely consequences of each of these levels of warming, and parties to the UNFCCC agree broadly that we really don't want to end up here, and we'd love to be down there, and we'll sort of settle for here if we can get here. So we get a goal. Right. We've got a goal. What are the targets that we need? So if we, say, agree the 2-degree target, then we know we can work backwards through the models that we use to make those projections to ask what's got to happen to the main driver of change, greenhouse gas emissions, in the case of climate change. And we can compare that to what countries have already said they're going to do. And so for 2 degrees, it's this greenish line here. And here's what countries have said that they're going to do, and it's not reducing greenhouse gas emissions anything like quickly enough. We have a gap that gets called the ambition gap, the difference between what everyone said they're prepared to do and what everyone agrees is necessary. That's the ambition gap. Everyone wants others to do it. Then there's also an implementation gap where this is what they've said they do and this is what's actually happening. And that's an implementation gap. And the two together, you get the emissions gap. So this is a really useful framing that shows whether progress is quick enough, whether it's, how close are you? Is the process apparently working? Do we need some kind of radical reshape? Can we do something similar for biodiversity? And schematically, we can, and Nick has. So these are sketches that Nick did. So we've got our idealized biodiversity index. It's been going down, as we've seen. It's going to keep going down if we carry on the trajectory we're on. we want to bend the curve, and if we can't bend the curve, we'd at least like to kind of hammer it flat. And we could see what countries' commitments through their NBSAPs are likely to lead to. Based on, again, an idealized driver intensity, a bit more complex because there's many different, much less commensurable, much less convertible drivers of biodiversity loss. But here's where we need to get to halt the loss, maybe the minimal acceptable outcome. Here's the trajectory that we're on if everyone does what they have committed to, and here's the ambition gap. Lovely. And then there's an implementation gap above it as well, but it's too small to get the words in. Great. Problem solved. So can we actually do this? No. So the session earlier was titled Prediction is Impossible. And that is true with these indicators. Now, I'm not picking on these indicators. These are just examples of indicators that are used and have demonstrated that we've got to do something. They've told us that we're in a load of trouble because we're losing biodiversity and its contributions to people very, very rapidly. Right. These come from a brilliant paper 10 years ago in Science that was looking to see whether we were going to meet the Aichi targets. And the way that they did it was they got together the best time series for the best indicators that they could, and then see whether they were going to actually do what they needed to by 2020. They sort of carried the line on, but expanded the confidence intervals. And they did this in a statistically rigorous, very defensible, very reproducible, sensible way. But these indicators are compiled after the event from time series data collected up to that point, and they look backwards. That is all they do. So they're not changing sign, right? Well, what if we did this? What if we made this policy intervention? Would that do the difference? No idea. Can't tell. They're not geared that way. They're not constructed that way. They're not so good for looking forwards. So I'm not denigrating those indicators. They're fantastic. And they are how we've built, in as much as there is a global coalition that we've got to stop nature loss. They're the reason. Big part of it. But to get to where we want to go, we need a sat-nav. Because a sat-nav doesn't only tell you where you are, it also gives you that transformational knowledge, in Anita's terminology, shows you how to get from where you are to where you've said you want to go. So, putting a little bit of kind of flesh on that bones, this is the conceptual framework that BES uses in its assessments. And I'm not obviously going to go through this in lots and lots of detail, but it's basically got components that are these boxes: good quality of life, direct drivers, nature, nature's contributions to people. And it's got arrows linking them. And the early chapters in the global assessment are all about individual boxes. And they're about the status and trends of indicators on the state. So the status of the system, that system knowledge, I think Anita called it. But the later chapters, what they had to get to was, how's the system going to work? What are the plausible futures for nature? And how can we get to a more positive future? And so those later chapters used models. Models are what link up the different boxes. We need to know more about the arrows, and that's what the terms in models represent. There's loads of ways of modelling biodiversity. I'm not even going to open that can of worms at all. Box of Delights. Always get those two muddled around. Yeah, Christmas Day goes really badly. So models are literally the only rational way of linking targets, policies, and indicators. So ideally, the way that you'd set a global biodiversity framework is you make your goal, you think, right, what actions can I do that will bring about that goal? Right. So I've got my biodiversity models. Here are my action targets. Let's run the world forwards. Are my indicator trajectories on track for the goal? If not, I haven't got the right actions. I need to adjust the policies. Keep going round, and maybe I've got to change the goal. Maybe it's not a feasible goal, or not a politically feasible goal. And then, hopefully, we reach a point where, yeah, computer says, yes, let's enact the policies. So at the moment, we don't have this for biodiversity. The indicators that can't be forecast can't help us with this process. As a result of that, it means that as well as the ambition gap and the implementation gap, we've got a framework gap. We could meet all our targets and miss the goal. Don't worry, that's not going to happen. We're not going to make all the targets. So the CBD have published the criteria by which they choose potential headline indicators. And I'm not going to go into these. They're all eminently sensible. However, modelability is not a criterion, and the word model does not appear in the Global Biodiversity Framework. All well-established headline indicators are compilation-based. They look backwards. They are about single boxes. Okay, biodiversity change is super hard to model compared with climate change. I've got a paper coming out imminently in Phil-Trans that goes into these in detail. A lot of them touches on points that have already been made, and others I'm sure will be made. I completely agree with the call for model into comparisons. And it's great that Inez is going to be talking about that. But if we do it, then we get the sat-nav for nature, because we enact the policies and we don't leave it there because our models are 20 years behind climate models. We need to monitor the bejesus out of what happens, not only to biodiversity but also to the drivers. That then goes back into improving new generations of models, hopefully augmented with a model into comparison program like there is for climate, and also then we compile the indicators that hold the feet to the fire and show whether or not we're there. Then we have that transformational knowledge, and we can get, hopefully, to a safe future. And I should have put up, but I didn't know, please don't post this picture on social media. I didn't know it's not mine. But basically, in order to navigate to where you want to go, you can't be looking only in the rearview mirror. It doesn't make any sense. You have to have a forward-looking road. So although prediction is accurate, precise, reliable, robust prediction is currently impossible, there is no alternative. I think we've just got to do it. Thank you very much indeed for listening.
Thanks, Andy, so much. We've got a couple of questions. First question is, when we think about the biodiversity indicators that we have, we've got indicators of extinction risk, indicators of species abundance. Are there some types of indicators that you think are intrinsically more modelable than others?
At different scales, yeah. Yeah, I think extinction is really hard to model with precision. So you need the law of large numbers to apply, and then I think you can model it. I think composition, structure, function indicators are probably easier. Abundance indicators as well, potentially. But I personally don't think, this is my own view, so I run phenomenological, statistical models. I think I agree with Damaris's point that models need to be dynamic for loads and loads of purposes. I don't think process-based models are the only way. I think you can fit statistical models that include within them the rates of processes that you know happen. I don't think that's a mechanistic model, but it can also be dynamic. But I think our difficulty is one of complexity, really. But one thing, when we monitor, we will learn so rapidly, because one of the reasons biodiversity is hard to model is it's not well mixed like climate is. But that does mean that when you've got different things going on in different places and you monitor it all, your knowledge of the system grows way more rapidly than knowledge of the climate system grows. So although we are at least 20 years behind, we have actually a very good chance of catching up if we set our mind to it.
Cool. Thank you so much. So at this stage, we're moving from more conceptual talks to some case studies. And our first case study is from Ines Martin, who's going to talk about a model into comparison project using global scale data.
Right. So first of all, I'm trying to give you a glimpse of something that took years to do in 12 minutes. So first of all, I'm very sorry if I talk too fast, but also I'm talking on behalf of quite a big group of co-authors and modeling teams that were involved in this process. So bingo, I got the figure as well. Usually I start this talk with describing what scenarios are, but I think we're quite confident right now and I can skip this slide. So I'll just give you a bit of a backstory for this exercise. So it'll be a bit of memory lane for a few. So with the rise of data availability and methodological techniques, scenario analysis became quite popular in the early 2000s. So a lot of biodiversity and ecosystem service modeling teams that were interested in global change gave their hand at it and tried to kind of assess how biodiversity or ecosystem services were changing. They were looking at different systems, different realms, using different metrics, looking at even different scenarios, and so on. So it was also became quite clearly, obviously, that when we're trying to get one message or one clear message or a few sets, it was very hard to come up with a clear indicator or number that uncertainties were not on the range of I can't say anything. So with that awareness in mind, actually, sorry, this was too fast. BES actually built an expert group on scenario and models and actually tasked its expert group to actually review what we have been doing and provide us as well with a toolkit of how we should actually, or how could we improve scenario analysis coming into a future and create these exercises actually being more useful and match the needs for decision makers. So the expert group came together actually with a lot of other modeling teams that were doing this kind of biodiversity and ecosystem servicing, assessment at the global level, and we built what we call the intercomparison of biodiversity and ecosystem service models using harmonized scenarios, or the BES. And this was a very long process that I'm not going into detail in the different steps, started almost a decade ago. But just to highlight that some of the results, I can say, did end up on the BES Global Assessment back in 2019, with the final set of results are only getting published early this year. And this is what I'll talk a bit about it. So, like I mentioned, besides bringing all these teams together, there were actually quite two big objectives of this exercise, was to actually predict what were the global impacts of land use and climate change on multiple facets of biodiversity and ecosystem services, and how they actually compare to historical changes or changes happening in the last century, and to actually quantify and understand how much the variation in the projected outcomes we were getting were actually due to the different scenarios we were exploring or due to the different methodological choices or models that we are using. And one key source of uncertainty that was actually highlighted in a methodological assessment back in 2016 was the fact that different modeling teams were actually using different sets of scenarios or different projections, how the future may look like when doing their assessments. So this is one big thing we wanted to control for. So all the modeling teams were asked to run their own predictions using the same set of scenarios to the future. And then here we use the SSP-RCP framework. And we choose 3 different, very distinct scenarios that allow to explore a range of land use and climate change projections. Also, another big source of uncertainty, people already touched a bit on this, was the scale of analysis that some of these models and predictions were being run. So we also control for scale, and we ask all the modeling teams to run their predictions at the global level, regional level, and at the local level, with these local level predictions also summarized at the upper levels. And finally, we had these 2 temporal scales, like I mentioned. We're interested, if possible, the models to run predict change into the past, as well under the 3 scenarios of future change. So just to summarize, we had the same input data. We came together, we decided on which data we were going to use. We gave all the modeling teams the same layers, the same information. We wrote a protocol and published a protocol defining the different steps. We had defining the models. We had about 8 biodiversity models altogether and 5 ecosystem services models, and a range of metrics that the different models could use to predict change. Not all models can predict change using all these different metrics, but we had a core set of models for each metric that we used to quantify global change. And this was a quite of interactive process back and forward with the modeling teams, but it was also our ultimate goal then to get all these outcomes from the modeling teams and provide summary statistics and intermodal means as well as uncertainty estimates. And this is just an example of some of the results we got. So for instance, this is for the global level projections. And here on the y-axis, we have 4 of the metrics that we use to quantify global change. In the x-axis, we have relative change per decade. Each bar here represents a scenario of change with the historical predictions represented with a yellow bar. The size of the bar is the intermodal mean across all the models, with the individual projections of the models actually represented with the symbols here. So when land use change is considered alone, we actually see that that biodiversity loss that was expected to happen in historical times is expected to actually happen at similar rates or slow down in slower rates under all 3 scenarios of future change, although biodiversity loss was expected to slow down the most under the global sustainability scenario, and even actually under some metrics show improvement and reversal of biodiversity loss. Moreover, when we assess the combined effect of land use and climate change, much deeper declines were projected to happen. Still, it's important to highlight that we also got different levels of change depending on the nature of the metrics we used to quantify global change. So for instance, metrics that were tracking global habitat extent or intactness actually predicted rates of change up to 5 times higher than metrics that were just tracking species richness. Still, it is important to highlight that for some of these metrics, even despite all these efforts of trying to minimize uncertainty that comes with the input data and some of the methodological choices, we still had quite a few variability on the different predictions of the individual models, a bit more than we're expecting, but still much better than that was being done before. Worth highlighting here as well that this is, of course, global trends. They do mask quite a lot of local heterogeneity that's happening, as we know sorry, this skip, I wanted to do the first one, this. So for instance, if we zoom in just for a scenario, which is even under the scenario with the highest land use pressure, we actually see when we look at the local scale that there's a lot of locations across the world that biodiversity gains were actually projected to happen. And I'm sorry, this bar didn't translate well between Mac and Windows. But believe me, blue colors is gains in or improvement of biodiversity. But again, when we actually look at the scenario with just climate change and land use together, we actually see mostly widespread declines being projected across space. I'll really glimpse really fast by our ecosystem services results, but again, this is the same type of graph for the biodiversity, so colors and symbols represent the same, but here we have a first set that just represents the material ecosystem services that we're tracking, and then the regulating ecosystem services that we're tracking. And for instance, similar to the biodiversity, we still project and observe quite a increase in the rates of provision ecosystem services, material provision ecosystem services, but again, at slower rates actually than historical projections. But again, under the sustainability scenario, we actually see the best news with the slower demand of material ecosystem services, and even the reversal of some of these provision ecosystem services, which means that it's actually, if we follow this scenario, we actually could have some recovery for these ecosystem services. So altogether, if we think about the implications or what we learned from this work, well, as expected, we did find that these alternative pathways of development do and can impact different components of biodiversity and ecosystem services in various ways. And climate change is in fact posed to become the most important driver of global change, surpassing even land use change by mid-century. And again, the differences among the models, even after controlling for all these different sources of uncertainty, still highlight the need to further refinement and calibration of these models, work with the modeling teams to try to document and control and hopefully harmonize the different assumptions and the different methodology choices that were done within the models to try to minimize other sources of uncertainty. This is not done. Just to highlight in the last minutes that we are carry on with the BES2024. I know, very innovative name. But again, has been highlighted with the keynote speaker yesterday and a lot of talks today as well. Even as well under this exercise, the scenarios you use are not really focused on reaching positive futures for nature. So what we hope moving forward is actually use the nature futures framework to create nature positive scenarios, and that will be the base of the scenarios that will be the base used for BES2024. We also want to as well explore that under these nature future scenarios, how we can reach the different global biodiversity targets like the GBF targets and the SDG targets. So this is a lot of what we'll be doing. Please don't take pictures. This is just a photo of how it looks like, even the complexity on a first level workshop of us thinking about it. But yeah, just to mention that this is still, it will keep going. And with that, I'd like just to thank you and thank everyone involved in this exercise.
So thank you so much, Ines. We've got 2 or 3 questions. So first question, can I ask you how you get land use data from the past and the future?
So this is projected land use changes. So within the consortium of this BES2024, there was including land use and climate change modelers. So we use land use harmonization from George Hurt, and this was done to actually create. This is model data. So there's another set of whole modeling teams that their own objective is to actually translate these narratives that very brilliant people come up with, and actually how can we actually have data, land use or climate data, that may reflect the choices made under these narratives. So this is the data we were working with when we're doing this exercise. But it's really well established data that translates quite well different of the decisions under the SSP RCP scenarios.
So given that you've got these different models and they're all uncertain, is it appropriate, and when is it appropriate to harmonise or produce some kind of ensemble prediction? When do you think that would be valuable compared with what you presented?
Well, I think, so the way we did this, this exercise, I think is very valuable. We documented, we thought at every stage of the process, we came together and tried to understand, okay, what will be potential sources of uncertainty. We were clear about it when we wrote the protocol. We say, this is the things we can control for, this is the things we cannot control for. But we are still doing very high level projections, and we don't try to sell it as something that it's very fine scale, very indicative of how it's happening at the local scale. So I think this type of analysis done at this level with this type of considerations, they are very informative, not only to provide with some guidelines of how some of these high-level decisions can impact biodiversity and ecosystem services, but as well to improve the next generation of models and scenarios.
Absolutely. Thank you so much, Shinesh. So that was a global case study. Again, can I ask people on the ends just to move in a bit to make space for those who are arriving? We've heard from Inesh a global case study, but the Global Biodiversity Framework will, of course, be implemented at the level of the party, the nation state. So our next speaker is James Bullock, who's going to talk about a UK-focused case study on projections of not just climate.
What do I do? Do I press a button?
It magically appears.
It magically appears, okay. It's on my screen here. Do I need to do something? Oh, something's happening. Whoa. Oh, there I am. Hey. Oh, exciting. Great, I can't see it here now, but never mind. Okay, yes, so as Nick says, I'm going to focus on a much more local scale than the previous talks. And this is work we did under what we call the SPEED project. You can see the acronym here. My surname being Bullock, project called SPEED. Sadly, we never got SPEED 2. That's my joke, which Nick has heard many times over the years, and he still hasn't laughed.
Because you're not wearing the right wig.
So I pressed the next button, and oh, nothing's happened. Shall I try again? Oh, there I am. Okay, so we've seen this sort of diagram before. You'll be very pleased to hear I won't be doing that bloody Leclerc diagram, so at least you can miss that on this talk. But what I'm going to focus on today is these sort of exploratory scenarios, which is looking at different assumptions about how might things develop in the future and where that might take us in terms of a number of outcomes and drivers. And if I was to be cruel, I would say that's like reality compared with dreams of target-seeking scenarios, and I think we've seen that a bit with the talks gone by. And this is a good way of exploring possible futures so we can see how policy options might react to those very different pathways, but also to actually see what the consequences are for things like biodiversity outcomes, what might be good and what might be bad, and how bad it might be. And in thinking about that, let's think a bit about the future. So the talk's called Not Just Climate. And for a room like this, when we think about the future, we will often think about climate, so things like that. But as already been touched on, the future also has many other aspects to it about how society may change, how technology may develop, how people may interact with each other, good things, bad things in terms of society and for biodiversity. So the future is not just climate, it's many other things as well, and how do we think about those? Now the SSPs, the Shared Socioeconomic Pathways, have been touched on, but not gone into detail, so I'll go into a bit of detail about those. The IPCC came up with two ways of thinking about the future. One was the climate futures, RCPs, we've all heard about those, 8.5, 2.6, etc. But also the SSPs, where they wanted to encompass a range of plausible outcomes, and I think Anita used the word plausible. So this is things that could happen plausibly, not saying they will happen, and people may have different attitudes about just how plausible or implausible they are, but they're sort of sensible, realistic. And these SSPs were developed on two axes. In IPCC speak, they're challenges for adaptation on the bottom, challenges for mitigation on the y-axis. For normal people, I think the way you think about it is the x-axis is how society is structured, how well it's going to be able to cope with challenges in the future. And I always equate that to equity. So towards this end, we have high equity, a well-organized society where everyone's contributing. At the other end, it's much more inequitable, is that the right word? And by that reckoning, very less able to develop responses to shocks and worries about the future. On the y-axis, challenges to mitigation, that's about resource use. So as we go up the axis, we're using resources more and more, and that could be fossil fuels, but also other aspects of resource. So SSP1 is what we call the sustainability scenario, where we're all nice and equal and equitable, and we have stopped screwing the world for its resources, and we're all living quite nicely. There's got we can develop scenarios around all four corners of this, and maybe a good contrast is SSP3, where we're very unequal and also we're really screwing the world for its resources. And the reason you have it's called regional rivalry, you see this sort of apocalyptic future, is because the projections are basically, as you get towards the end of the century, you get societal breakdown because we've overexploited things, people are rebelling, etc. And so it's a very negative future. But there are many others, and there's also, just for a bit of baselining, is SSP2, which is the the middle of the road of all of these things. So what the IPCC Community Scenario Framework does is take those climate projections, 8.5, etc., and these SSPs, and I think Inesh mentioned this, you put them together in plausible combinations and use those, as Inesh showed, to look at possible scenarios for the future. So we've used this approach, but we've gone a bit differently to what's been talked about before. And what we were wanting to do in this project is to look at how different aspects of the environment might change under these plausible scenarios, but not just how they might change, but linking these together so they're plausible in relation to each other as well. So what we did in SPEED was produce spatially explicit projections, i.e. maps, of a range of drivers under these different scenarios over the next several decades. So we start off with the IPCC scenario framework, SSPs, RCPs, and we use those to project what would happen under land use change, and I'll describe that in a bit more detail. And then we've got a couple of other outcomes and drivers. Outcomes become drivers, and we get a bit of a looping. What we don't have is feedback, which would be fantastic, but we haven't done that yet. So that land use change, climate, social change affects pollution in various ways, and those can all feed through to affect biodiversity. And so in UKCEH, we came up with this. There are other things you could look at, like invasive species, what happens to water resources, etc. This is not comprehensive, but it was a thing we could do using the resources available, and also using really expert teams within UKCEH and also collaborators. And what's really cool about this, I think, is that we use very different methods for each of these things. So climate scenarios, we use what the Met Office had done, but we do statistical downscaling of process models. For the SSPs, we use participatory approaches to develop scenarios of what happens under these different futures. Land use change is agent-based modeling. The pollution is process modeling of what happens to different pollutants under different scenarios. And biodiversity is statistical modeling. So one of the things cool about this, we're bringing together different approaches, whatever each team uses in their everyday work. And so it's actually, what's the type of disciplinarity that is? I can never remember. But it's basically bringing together different disciplines rather than me trying to do everything myself, which I think is quite cool and really uses that skill set. So what we do from that is we get different outcomes, different sets of outcomes. So we've got climate projections, I should say, and that all of these are or will be available for anyone to use, open access, all the data, etc. And certainly the climate stuff is. And I won't go into great detail, but it's projections for different climate variables under different of the RCPs into the future. And I've highlighted the maps here of extremes, because I think that's one key thing we need to think about in Biodiversity Futures as a digression, not just averages. The SSPs, the socioeconomics, as I said, we developed those quite differently, but we've got a range of different outputs, detailed narratives of how society, tech, population, etc., might change in the future. And we use methods to make what we call semi-quantitative trends of how a range of different variables would change under the different scenarios. And actually, for some of them, we could then do spatial quantifications using different methods. And all of that is published as well. What we do then is take those climate and societal futures to project land use. And this is working with the Edinburgh team, with their crafting model, which has been mentioned already, which is an agent-based model, where basically what we do is use climate to say how suitable the land is for a range of different land uses, and then use the socioeconomic future scenarios to say what do society want for the land. So you have, and this shows those plausible combinations. So you have RCP 2.6, the low climate change, with SSP 1, the sustainable future, and that has you can see the different land uses projected. This is by 2080, I think, but we've got time steps. And then as a contrast, you've got very extreme climate change with this SSP 5, which is where we're really exploiting our resources, but also society is fairly stable and able to keep going until we really screw everything up. And we've got a range of outcomes. You can see there's sort of quite a lot of variation amongst the maps, and that gives us a basis for looking at a variety of other things. And I mentioned pollution and biodiversity. I'm not going to go through each one and describe in detail, but just to say we've got quite a lot of outputs, some of which are published, some of which are in development. And that's why I've said don't tweet this or whatever you want to do, although it would be totally incomprehensible if you did. But some of this is in development. But just to really demonstrate, there's quite a lot of outputs, and I think that's a great thing about having a really diverse team of people, experts working on this. But those lots of outputs are summarized here into a very partial summary of those detailed results. And it's certainly not everything that we've projected in the future, but just to demonstrate what we can do with this approach. So we've got the RCPs down there, the different climate scenarios, SSPs 1 through to 5. And we've combined them in plausible ways. And what we get is outcomes. So we've got fairly obvious arrows, big increase, somewhat increasing, big decrease, somewhat decreasing, and some staying about the same. And we've got these, what would happen, what's projected to happen for climate, various aspects of climate, aspects of socioeconomic futures. I think these are just quite interesting ones for an audience such as this. You can see quite a lot of different outcomes. What happens to different aspects of land use in these different futures, pollution, nitrogen, heavy metals, etc. And you can see they're not all doing the same thing, they go in different directions. And the biodiversity outcomes, I think maybe to linger on that, this is work that Rob Cook is still writing up, Rob, if you're in the audience, but it'll be off soon, I'm sure. But quite interestingly, we get different outcomes under the different scenarios, but also different outcomes for different aspects of biodiversity. So just to really summarize that it's not straightforward futures and not obvious ones either. And this is to say, thanks very much to the team of people within CEH and also the partners who we worked with on it. I'm just going to finish off by digressing slightly by saying that if as scientists we want to move beyond just telling people what might happen and giving policymakers and decision makers information and want to actually try to make that change happen, one approach is advocacy and activism. And if you're interested in that, we've got a new network on that, BES network, which is just starting up, and you can come along and meet us at the Meet the Networks between 6 and 7 this evening. Thank you.
Thanks so much, James. So we've got a couple of questions. First one, this is very terrestrially focused. What's the possibility of doing this sort of thing for the oceans?
I think it's very possible. I mean, obviously, we've got climate projections for the oceans. basically, the other aspect is these sort of SSP things, and because it's through expert elicitation, I didn't go into great detail about it, but you get a bunch of experts in the room from different sectors, and you start really trying to develop what futures might look like under these different sets of SSP ideas. So we could certainly do that for oceans, because, are we going to carry on exploiting? Are we going to protect them? What's the impact of aspects of pollution on the ocean? So definitely it could be done. I agree it's very terrestrial focused and actually not even very freshwater, but certainly these things are very possible.
Very quick question. Yeah, it's the question about the downscaling of the SSP narratives, and can you just very briefly talk about who participated in that?
So we had people from a range of different sectors. There's quite a lot of academics involved, because they all come along to these meetings. But we had people from policy, from industry, from NGOs, etc. And I guess for a non-social scientist, that may sound a bit random, but basically we get people together who represent different sectors, different ideas, and there's quite a lot of framing going on, saying this is what's gone before. So we set the UK SSPs within the European SSPs, which had been developed before, within the global SSPs. So it's got to be coherent. It's a sort of strong word we use. It's got to be linked to that. So it's not like just people running off with their imaginations. It's actually thinking about what aspects of society, etc., might change and what it might look like under these different scenarios, and keeping everyone on line of that, and actually looking for consensus and also seeing where disagreement comes up. So it's not my expertise, but it's quite a complex process with facilitation, etc. And also we then go out and check them. And what amazes me is how remarkably consistent they are and how we actually get very coherent outcomes from it.
Cool. Thank you so much, James. So Damaris told us that there are both process-based and correlative models, and most of the examples that you've heard thus far have been statistical correlative models. But Greta is going to talk about the potential for using process-based models.
Yes, hello. So normally I would start with say, okay, these are our questions. How species will respond to different interaction impression, and how best do we manage this response? And then I will go on and say we can use model for that. There are different models, correlative, process-based, how they compare. But Damaris already done that very, very nicely. So I deleted all these slides. And I just put these one slides that, kind of summarize again what Damaris says. And this is a paper that just came out last week from Mark Urban in Science, where he did a meta-analysis. He summarizes more than 5 million projections, I think, on extinction risk. And he summarizes, well, the models that were used. And again, we have these figures that more than 18% don't contain any mechanisms. While now we have a rebouncing after the early 2000s, when we had the explosion of correlative models. We have a rebouncing of models that contain some mechanism, but maybe one or two, but very, very few models that contain more than that. And demography and dispersal are taking kind of a large part of the mechanism that now are more integrated in this process-based model. So given that everybody has done a great introduction, I jump straight into one example of this process-based model, which is RainShifter, which Damaris mentioned. RainShifter was developed initially by our team in Aberdeen, 2014 was published, and then we pair up with the Damaris group in Potsdam, and in 2021 we released version 2 that was also come up as RainShift R, so R package. What is RainShifter? Is basically an individual-based modeling platform integrating a few processes. At the core, we have demography, which can be stage structure, and you can implement different level of complexity of stage structure and demography. Dispersal, where you can simulate movement mechanisms, or more phenomenological dispersal kernel. And genetics. And in particular, we are about to release the version 3, where genetics is much improved. You can explicitly simulate a simulated genome, and you can model neutral markers, but also accumulation of genetic load and some trait evolution, and thanks to the work of Theo in Aberdeen and Jette in Potsdam. And this is very much work in progress. RainShifter is a single species model so far, but we're really working towards integrated species interaction and making it multi-species. So hopefully watch this space. So what I do, what I would like to do for the rest of the talk, given I only have 12 minutes, is giving you a few examples, and really here we focus in a more local scale, regional scale. So an example, our rain shifter has been used for regional projection under alternative management scenarios. Again, regional projection, but now integrating climate by linking demography and environment. And finally, a proof of concept example of how we can link different type of models, in this case, population model and land use models, to get at the feedback between land use change and population responses. So the first example was done by now ex-PhD students Benjamin Blyle in Berlin, and he was looking at the Persian leopard in the Caucasus and was really interested in asking, through modeling, the potential persistence and potential expansion of the leopard in the Caucasus under different scenarios of reduction of human persecution and prey restoration. So this is the study area, so this is the Caucasus, this is an habitat suitability model that Ben built. And you can see that there is quite a lot of dark green, so quite a lot of potentially suitable habitat for the Persian leopard in the Caucasus. But the current distribution is limited to the south, so basically Iran and a little bit Turkey and Armenia. So Ben used the habitat suitability model as an input for rain shifter, then parameterizing dispersal and demographic model for the leopard, and run the model with different scenarios on a 100-year horizon. And so we have low to high prey restoration and low to high reduction of persecution. And you can see, and you can see occupancy probability in the map. And you can see that no matter prey restoration level, if you don't reduce the persecution of only a little bit, the model predicts the leopard to go extinct from the region totally in under the horizon. Under a medium reduction of persecution, again, no matter, well, do a bit better in high prey restoration, but basically hangs on in the current distribution. It is only when you really crack down persecution that then it can thrive and potentially expand. Second example is, again, from another ex-PhD student from University of Kent, Dave Seaman. Now we are going in another part of the world. He was working with orangutan, was still working with orangutan in Borneo, and he was interested, again, in exploring different management scenarios, in this case, in high modified oil palm modified landscape dominated by oil palm plantation, and how different management scenarios impact on the orangutan population. So this is the study area, and up there in Sabah, Malaysia and Borneo. What you see here, all the yellow is oil palm plantation, and then you have the green, which is forest cover, which is potentially suitable given a certain size to sustain orangutan population, although these small fragments are considered not suitable for the orangutan, so they are deemed potentially disposable, right? Potentially convertible in plantation. So they run the model under different landscape scenario. The worst case scenario being land sparing, where you only conserve the forest in strictly protected area, and you get rid of basically all the fragments of forest that are in the middle of the plantation, all the way with a gradient of increasingly conserving fragments of forest of a certain size within the plantation. And again, I'm going to run quickly through the results. These are the results summarizing these very nice figures. I really like it. But what you see here, the gray patches are the forest, the dots are population, proportional to population size, and the thickness of the lines represent the fluxes of individuals between different populations. What we found is that under the land sparing scenarios, there is very limited connectivity. So there is a lot of dispersal mortality, and dispersal mostly recruit back to their natal patch, so there's not much flux of individuals, and individuals are confined in protected areas. when we conserve a little bit of the biggest patches, increase connectivity, but population size still not increases. And it's only when we conserve, not all, but a good proportion of these little forest patches that we have much increased connectivity, much more successful dispersers, and also increase in population size. So the conclusion is that this potential for humanly defined landscape to support orangutans population, provided that these fragments that are deemed potentially not suitable are conserved. Oopsie, too fast. Third example actually comes from Damaris group and Anne that built the rain shifter. And here is really looking at how we can integrate climate in demography. So the impact of climate in demographic parameters and variable. So what they did is they did these studies for 8 Swiss breeding birds. And they create this very nice pipeline. We have rain shifter here on your right. But what they did is then they used survey data, occupancy and abundances time series to calibrate demographic climate relationships. So how adult survival, how juvenile survival, how fecundity changes with climatic variable. And then feed this relationship into rain shifter and run the projection. Again, for sake of time, I won't go so much in the detail, but what they get is maps of, as I said, juvenile survival, fecundity, adult survival, how do they change in the environmental space, fed that into a rain shifter, how do the projection perform, and they found improved prediction in temporal trends, not necessarily in spatial pattern, which what Tamari already discussed in her other example. But this relationship also allows you to have a mechanistic understanding of the causes of the demographic suitability of the different region. But also like missing knowledge. So some of the demography environment relations were a bit wonky and not really plausible, and that highlight where we didn't have enough knowledge to parameterize that. Finally, very quickly, an area that I think is super important and super interesting, there's a lot of potential there, is getting at the feedback between not only biodiversity processes, ecological processes, but also with the drivers. And in this case, land use is a complex socioeconomic system. And here, again, an example done from an ex-PhD student, Nick Sainz at the University of Southampton, that did a loose coupling between rain shifter and the crafty model that you already heard a couple of times about. So this agent-based model of land use. And what a loose coupling means is that it did an example, a virtual example of a pollination population and crops. And so what loose coupling means is rain shifter runs the population dynamics and dispersal of the pollinators, and in each type step feeds the distribution of the pollinators to crafty, and so that will impact the level of pollination of crops. The farmers then makes some decision according to the yield. Land use may change, and that's feedback into rain shifter in this cycle, so we can get the feedback between land use and population dynamics. And in this, so in the climate also comes in directly because it influences the suitability of the pollinator, but it also influences the yield, but also indirectly, because by influencing the yield, influence the decision of the farmers, and then little change of the land use, but also by influencing the pollinator, it affects the level of pollination. And then so we get the gist. So in this theoretical example, they run the uncoupled model. So uncoupled would be if you run rain shifter first, feed the output into crafty, and see how that change, or the coupled model as I described under a particular scenario of climate change, but that's not too important. But what's important is that the difference between the two models. So accounting for the feedbacks predicts a higher conversion of pasture and natural habitat in crops. And that's driven by the effect of climate change in that particular scenario on reducing the population of the pollinators and then increasing the demand for land conversion. So I would like to finish at that. Thank you, and reiterate, if you want to join EcoCode in this endeavor, modeling endeavor, please contact us.
So we've got time for a couple of questions. So one is about scale. So the examples are typically sort of regional scale. If you were to scale up to thinking about scaling up globally or multiple species, are the barriers simply computational, or do you reach some sort of conceptual barrier?
I'm not sure so much about conceptual barrier. I think the barriers will be computational, but that I think we can address, because there are different techniques that we could do to address that, but also it would be a bit data, I guess. So the challenge, I guess, is scaling this type of model to a lot of species, more than the spatial scale, I would think. We are getting there with the spatial scale, I think.
So the other question is about uncertainty in parameter values and how you can, what is the practicality of doing sensitivity analysis?
Yes, I haven't talked about sensitivity analysis, but sensitivity analysis should be kind of a, I missed the English word, but something that you always do, right? To assess how sensitivity is your model to different parameters. And then also with methods of calibration, we can address the uncertainty. So I think the nice thing is that we can expose the uncertainty with this type of model. And we should also strive to expose it and not just ignore it.
Thank you so much to Greta. So in our final session, final talk of this session, we are coming right down to a UK really tangible example focusing on the effects of protected areas on birds in the UK. And I'm delighted to welcome Jenny Border from the BTO.
Hello. So the work I'm going to talk about here is part of a much larger project called the Biodiversity Pathways, which Nick introduced briefly earlier, but as you might not have all been there then, I'll go through it again now. So this is a collaboration between the Centre for Ecology and Hydrology, the BTO, the Joint Nature Conservation Committee, and the University of Cambridge. And this project aims to build UK capacity for modelling biodiversity futures, and so enabling us to better predict how biodiversity might change under different scenarios of environmental change. We wanted to make this work highly relevant, so we've been working closely with the devolved administrations for each country and with the national statutory nature conservation bodies to ensure that this work is relevant to them and that it tackles questions that will help them to implement solutions that will reduce biodiversity loss effectively. So this project consists of 4 work packages, but here I'm just talking about one work package, which is where we explored using evidence from the past to predict the future. So firstly, a brief introduction. As you'll all know, biodiversity is currently being lost at an alarming rate. There's been various different published analyses covering a whole range of taxa that have shown that protected areas could reduce biodiversity loss. So an example of one of these is a paper led by my colleague Ailey Barnes, which compared bird abundance, trend, occurrence, colonisation and persistence inside and outside of protected areas. So the graph here is from her paper, and it shows that in sites with higher protected area coverage, species occur more often and in higher numbers and are more likely to persist at or colonise sites. So at the UN Convention on Biological Diversity in 2022, governments from around the world committed to increase protected area coverage in their respective countries to 30% by 2030, or 30 by 30 for short. But there are many different ways that this extra protected area coverage could be implemented, and these will vary in how effective they are at halting biodiversity loss. So therefore, for this part of the project, we aim to examine the effects of different ways of implementing 30 by 30 on UK bird abundance and trends. So the bird data we used in this was from the BTO JNCC RSPB Breeding Bird Survey, or the BBS for short. So this survey has been running since 1994, with between 1,500 to 4,000 1 kilometre square surveyed per year. And this gave us a really good index of species abundance for all the surveyed 1 kilometre squares. And then for environmental data, we extracted data on the topography, location, the percentage habitat cover, both within a 1 kilometre square and immediately surrounding it, and habitat diversity and whether a square was part of an island or the mainland. For the habitat data, we used the CEH land class data, so I've just shown that on the map on the right here. So now on to the protected area data. So in case you don't know, protected areas are classified into 6 different IUCN protected area management categories. So the map on the right shows the distribution of these in the UK. And these classifications roughly span a distribution from the more natural areas, which tend to have lower numbers, like 1 and 2, to the more heavily modified sites, which have the higher numbers, like 5 and 6. Also, categories 1 to 4 are more highly protected than categories 5 and 6. And several studies have found that category 5 and 6 protected areas are ineffective. So here, we've only included categories 1 to 4 as protected areas. For this analysis, we're focusing on 30% of the land surface area, so we've only included terrestrial protected areas. And then we calculated the percentage cover per 1 kilometre square for every 1 kilometre square in the UK of protected areas, and the percentage cover of protected areas in the surrounding 1 kilometre squares, so immediately surrounding each 1 kilometre square. So now we've been through all the input data onto the modelling itself. So just a reminder here, we're aiming to model species abundance under the current situation and then predict how species abundance might change if we increase protected area coverage to 30%. So we ran individual species random forest models for 161 bird species. And so we modelled the species abundance against the environmental variables I mentioned earlier, year and protected area coverage. We then used these models to predict 1 kilometre square level abundance under the current situation with the current levels of protected area cover for each country. So the map here shows the different protected area coverage for the different countries in the UK. And you can see England currently has the lowest percentage cover with only 8.1, whereas Scotland has the highest with 14.6. And then we predicted the square level abundance under 4 different scenarios of increasing protected area coverage to 30%. So these scenarios by no means covered all options, but we chose them as a balance between what would be most useful to illustrate different planning principles and what was feasible to implement in the time we had for this project. So in the first scenario, we assigned extra protected area coverage randomly for each country, in units reflecting the mean protected area coverage of protected 1 kilometre squares in that country. The results shown in the map here, and the percentage protected area is shown in blue. In the second scenario, we added the additional protected area to the biggest existing protected area in each country. So we were trying to make the protected areas as big and continuous as possible, building on Lawton's principle of increasing connectivity by making protected areas bigger. I should say these scenarios are not necessarily meant to be realistic, so we're not saying that we're trying to protect the whole of North England. For scenario 3, we explored a scenario we thought might be easier to implement practically in the UK, which was changing all the IUCN category 5 and 6 protected areas to categories 1 to 4. In this scenario, the amount of protected area per country only equals 30% for Wales, as there wasn't enough existing category 5 and 6 protected area for the other UK countries. So in Scotland, only 20.5% is protected, in England 28.3%, and in Northern Ireland 29.4%. And you can see how these are distributed on the map here again. So in the last scenario, scenario 4, we aim to maximise habitat representativeness in protected areas. So here we calculated the percentage cover of each of the 9 land-based habitat types that we included in our analysis for each country. Then we worked out the percentage cover of these habitat types in protected areas for each country. And then we aimed to add new protected area to increase the representation of the underrepresented habitats. So in our case, this mostly meant adding a protected area to arable areas or to towns, urban areas, But there was also, so in Scotland, that also included added woodland. So on to some results. This is still very much a work in progress. We've only been working on this for the last couple of months, but hopefully it can give you an indication of what we might see in the final analysis. So firstly, as we hoped, we found that adding new protected area increased abundance for the vast majority of species that we included. So a quick reminder here, we included 161 species. So the graph here shows the number of species where increasing protected area cover had positive effects, so increased species abundance, or negative effects, so decreased species abundance. The different colours show the different scenarios. So orange is no spatial targeting, blue is expanding existing protected areas, green is converting the category 5 and 6 protected areas to categories 1 to 4, and pink is maximising habitat representativeness. And these are the mean values across all 4 countries in the UK. So from this, you can see that no spatial targeting affected slightly more species negatively than the other 3 approaches, and expanding existing protected areas had slightly more positive effects. But the results are pretty similar between the different scenarios. However, if you look at abundance for different species, then the results are a lot more variable. So we don't have time to go into all the different species here, but if we look at abundance gains for each scenario, taking the mean across all species, so this graph shows the mean percentage change in abundance under each scenario in each country over all 161 bird species. And the colours, again, are the different scenarios. So here we found that expanding existing protected areas led to the highest mean abundance gains for all countries in the UK, apart from Scotland. And in Scotland, increasing habitat representativeness of protected areas led to the highest gains instead. This scenario was the second most beneficial for England and Wales. So that's a very brief look at some early results, but now on to a few things that we have planned for the future. So far I've talked about changes in abundance under increases in protected area coverage, but we also plan to look at changes in population trends, particularly because abundance can just reflect where protected areas are designated initially, rather than the effect they might have. And also, so far here, we've looked at the contribution that increasing protected areas could make towards our biodiversity targets. But we also want to look at the additional effects of improving the condition and the management of these areas. So the condition effect is based on a paper led by another of my BTO colleagues, Caroline Brighton, who found that protected sites with favourable condition had more bird species showing positive trends than protected sites with unfavourable condition. So we're using some of the metrics from her paper to try and see the effect of improving condition and adding that onto our different scenarios. And to look at management, we're working with the Cambridge Conservation Evidence to derive some effect sizes for the impact of different levels of habitat management. And again, we'll be adding this onto our scenarios. So that's all for now, but watch this space, because we're aiming to complete this analysis by the end of March next year. And thanks very much for listening, and thanks very much to our advisory group for all their really valuable input into planning this work.
Thank you so much, Jenny. We've got lots of questions. Does the fact that you didn't get big differences between the scenarios imply that the UK is not doing a great job in terms of conservation?
I don't know if it would say that. So the scenarios are things that haven't happened yet that we'd be predicting. And there were differences if you looked at individual species level. I think it just sort of showed that they were having positive effects, but anything increasing protected area was really helping, as opposed to not doing anything. So it probably shows that if we just increase protected areas, we'll do something good anyway. And the type will help, but it's maybe less important.
So there's a question here about resilient networks, which is the kind of principle of the Lawton report, which you mentioned. Could you use the scenarios and models that you've done to think about whether the network we do have is resilient? Is that something that sort of can be mapped on to what you've done?
We can definitely we've got relatively simplistic models really. So we've got the amount of protected area in surrounding landscape and within. So Actually putting on the entire system would be quite difficult. I'm not sure quite how we'd integrate that yet. The current ones do have some indication of what connectivity nearby, what the effect it has, but I don't think you could get the entire corridor of networks on within the scope of this project. But it'd definitely be something really interesting to look at.
There's a question about the definition of protected areas. So there's a recognition that 30 by 30 will probably count things like other effective OECMs, other effective area-based conservation.
Yeah.
So is there a way to capture those in the analysis that you've done?
Yeah, we definitely were. Initially, we were planning to look at OECMs or some of the planned proposed sites, but the problem is the data's not really there yet. So we've been working with the statutory nature conservation bodies, and some of them have polygons of where they're planning to put it, but most of them don't. So ideally, yes, but we don't currently have the data to be able to do it yet because it's not enough information on where they're going to be.
Final question. You talked about connectivity in the context of the scenarios and the way that the protected areas are arranged, but was connectivity accounted for in the modelling framework?
Well, in the sense that we looked at the surrounding protected area and the surrounding habitat, but not further than that. Like ideally you would use something like Circuitscape, which I heard some really good talks on yesterday, and have that integrated in. So yeah, in a limited sense.
Yeah, cool. Brilliant. Well, thank you so much to Jenny, and thank you to all of our speakers. It's been a fantastic, informative session for me, and I hope for all of you as well. So thank you to everybody who spoke and to all of you who've come today. Let's give everyone a big round of applause.